Hello, everyone. How are we doing today? All right. My name is Nathan Thompson. I'm here to talk about Calculus 3. I hope that's why we're all here. I didn't get to verify that I was actually in the right place before this started because of the weird internet thing that happened. Um, but so the plan for us in here, of course, is to finish the standard calculus sequence. Um, We're coming off of 2 previous semesters of calculus where you met for 5 credit hours worth a week. Ideally, that would have been maybe the meet for 50 minutes a day, 5 days a week situation. Sometimes people do the 3 day a week version of the class. That's fine too, as long as you put in the work and develop the necessary skills and all of that. For us, we are here for Calculus 3. Calculus 3 is a 3 credit hour class. So, and in the format that we have here with our live time together, we're going to be meeting 50 minutes for 3 times a week, um, which has its benefits. I don't think it's as important to have the 3 time a week structure as it is to have, say, with the 5 for Calc 1 and Calc 2. But anyway, that's just minor stuff. It makes some things easier for the schedule as far as like section per day sort of stuff, but there are times where the 50 minutes is going to creep up on us because some of the examples take a long time to work through and we might run out of time and have a little bit less time to focus on a specific thing during one day than maybe we'd like. But we'll work through that. Um, Overall, there's something that you should know. Calculus 3 has concepts that are new, but it's mostly taking in and expanding upon ideas from Calculus 1, Calculus 2, and then also some ideas from vectorization and linear algebra. Okay. Um, One of the interesting things about the way that math courses are structured is that beyond Calc 2, you have some freedom in terms of what your path allows you to do. Okay, you're allowed to take differential equations, you're allowed to take linear algebra, and you're allowed to take this class, Calculus 3. Since Calculus 3 is the third of the calculus sequence, it seems like sort of a natural thing to do in order to take this class next. Um, a lot of my colleagues and I mostly agree, though a little bit less strongly than they would suggest this class is actually greatly supplemented if you take linear algebra at the same time. There are a lot of ideas that cross kind of back and forth, but that's not necessary. And also, if you're a little bit worried about linear algebra or something, that's a lot of math for that semester for people who are worried about that kind of thing. It never really bothered me, but I'm here teaching a math class, so different experience. But one of the things that I will do as we progress through the semester is not shy away from explaining where this cross pollination of ideas happen. Okay. Textbooks for most subjects have a tendency to try to be as self-contained as possible and not stray into those other categories. All right. I think ultimately that does you a disservice because it lessens your ability to see where these connections happen and how these ideas interrelate. So I will be mentioning these things, and some of it is just for sort of texture and context. Other stuff will be very important to understand. It will make your life when you take those other classes significantly easier. Okay, because it won't be the first time you've heard of this idea, and it'll put everything in sort of the broader mathematical context, and it will make things easier to remember when it comes back that you need these skills. Because you're not going to need some of the stuff that we're going to be talking about maybe in the next 12 or 18 months or whatever in practical experience, but 3 or 4 years down the line, you may run into it's like, oh, I should remember this because I've seen this before, and recapturing those details will be easier the more ideas in your mind that are connected to that web or that network of thought. So that's what I'm here to do. Okay. Now, what we're going to spend a lot of time in class working through, of course, is the technical details of how to solve problems. All right. Now that's sort of what most people want to see. They just want to see a lot of examples so they can learn the patterns and copy the patterns and do the dance and work through and do all that stuff, because that's how you get good grades on tests or whatever. All right. Now, that stuff's important, and we're going to spend a lot of time on that. But if you don't have the framework to contextualize those patterns, those skills, those techniques, you're not going to remember how to use them properly when it comes to a situation where you're under pressure, like we're taking a test or something. All right. So building that library of ideas and understanding where these things fit is the actual challenge of this course. Okay. We're going to have a lot of notation, we're going to have a lot of vocabulary, and we're going to have some theorems that seem difficult to understand or to see until the pictures and the ideas and the notation and all of it fits together. All right. The other thing that we're working against is some several 100-year-old at this point ways of writing things down. Okay. The people who invented a lot of these things were very pithy about how they wrote it. All right. They wanted short, compact expressions, and they hide a lot of details into those expressions. So we're going to be kind of pulling those things apart, expanding them, explaining what the notation means, because when this hypothetical 3 or 4 years down the road, you're looking up these ideas after having taken this class and are using this stuff, what you're going to find are the short formulas that don't make sense unless you remember what you're doing. Okay, the ones that have the cute vector notation and boldface symbols mixed with non-boldface symbols and dot products sitting in the middle of stuff. Why is there an integral sign here? What is this for? What does this mean? All right, so we're building all of this up. So, does all of that make a little bit of sense? Okay. Now, I also will say that I'm going to have to ask you to definitely, for sure, remember how to differentiate and integrate things and find limits of stuff. All right. Limits are a little weird because we have some extra rules to follow. We'll get to that in a few sections from now. But the way that the book is written and the way that the problems are structured is they'll throw the new notation at you for the calculus 3 stuff and expect other things to fall in place. All right. I don't have any issue answering questions about these things to get everybody sort of reorganized and realigned or recapture some of these skills, especially if you maybe took a semester off taking math or something. I know that happens every now and then. But those things are important. Okay. So what I will ask you to do this week, either Wednesday or Friday, I haven't decided what day I'm going to do it yet. But we're going to take a pretest. Okay. We're going to have some old stuff from Calculus 1 and Calculus 2 on there, all right, to serve as an assessment for everybody, so that you have an idea of where you are, I get a little bit of an idea of where you are, and if there are things that need to be worked out, then that gives you time to start working on those things. Okay. So that will be coming. I don't know if we'll do it on Wednesday or Friday, but we'll do it. We'll do it by the end of the week. Okay, so that's my opening statement here. I was going to talk about some stuff in the syllabus, but my copy of syllabus is on Blackboard, which I can't get to right now. The internet's down. They did something to the network about it about 10 o'clock. I don't know what they did. Because I opened my laptop, I tried to check my email, and then I tried to update my software that I use to organize this stuff, because it sometimes updates and breaks things, and I wanted to break it before class if it was going to break. And then the internet just didn't work, so here we are. Okay, so I'm going to, from memory, talk about some syllabus things. All right. I would point to specific parts of the syllabus, but we'll have to go through that as it is. Okay. So first off, we'll talk about homework. All right, I am for this class not assigning online homework, okay, in the sense of you log into some website and do problems on the online homework website, okay. We will be submitting assignments online through Blackboard, okay. Um, the way that that's going to work for, okay, let me talk about the other thing, then it'll be easier to talk about the homework. Okay, so I sent an email about this before the weekend. I'm using one Blackboard section to manage this in-person class as well as an online section. Okay, for the most part, there won't be very big differences between these two things. I will be very specific about the differences when it comes to that. I'm still considering for this in-person section giving short paper quizzes on Fridays. I haven't decided that yet. Okay. The thing that I will definitely be doing is for the online class, they will have short online weekly quizzes because I have to give them their stuff online. I might do the same thing for this class if I think that we need that 15 minutes just to have more time to talk, or I might mix and match. I don't know exactly yet. Regardless of the format that I do the quiz assessment part, the way that the homework is going to work is in the back of the syllabus, there are problem lists. Okay. The problem lists are exercise, like the minimal amount of exercises that you should do per section to keep up with the material. Okay, now I'm only assigning between 7 to say 12 problems or whatever per section. All right, you should be doing more than that. All right, but I'm trying to give you a somewhat representative sample of what's going on in the homework. Okay, the quizzes will be based on that selection of problems. All right, sometimes it'll be one or more of those problems. Sometimes it'll be problems that are related to that problem set. Okay, but you need to, of course, be making sure that you're putting in the other time, reading through the material in the textbook itself, checking things out, working through everything that needs to be done in order to keep practice, get used to the notation, all of that. Okay. In the homework lists, there are what I call starred problems. I have a little asterisk next to them. Okay. Those are extra credit problems. All right. If those problems are worked completely correctly and submitted with your quiz submissions, then I'll add points to the quiz. It's going to end up working about to be like +1 per extra credit problem or something for the quiz. So most of the points on the quiz are the quiz problems itself, and then you can get a little bit of a bonus there. Okay. Sometimes these problems involve the use of technology, okay, like online graphing equipment or something like that. Sometimes these problems are more theoretical, not quite proofs, but more along those lines, or more technically challenging versions of the homework problems. Okay. If these problems are going to be things that I'm going to ask test questions about, or I'm going to ask parts of test questions about these would be something that would be thoroughly reviewed or explored in lecture and review and things like that. Okay. But that's what's going on with those. Questions about that? Yes. Okay, though that's two separate questions. Okay, so the answer to your first question is on the homework where I ask you to use some kind of graphing utility. The ones that I'm going to recommend that I would demonstrate right now, but I can't because the internet's broken, are things that you can find online. All right, there's no need to pay for anything. All right, if you have access to something like Mathematica or some other software suite that can do these kinds of graphs, you can use that. But the things that I'm going to use are going to be freely available web interfaces. For exams, I am almost certainly going to ban calculators. Okay. there are two reasons for this. Number one, most of the calculators that people own can do calculus, and calculators have only gotten more sophisticated over the past 5 or so years. And I have also dealt with an unfortunate amount of people using banned electronic devices during exams. It's much easier just to ban them outright. Okay. Now, that comes with the trade-off of when I write exams, I don't ask you questions that require calculators, and I also build that into the complexity budget for the exam when it comes to what kinds of questions I'm asking. All right. The integrals and the derivatives that I ask you to compute aren't that hard if we develop the skill set that I mentioned earlier. Should be background stuff. So there's a trade-off there. All right. The the short, cute way to answer that question is I want to know what you know, not what you can type into the calculator. All right. I'm not assessing it. One of the things that's important to assess is your ability to interface with technology, because you will be using technology to solve problems. All right. In-class written exams are not the place to assess you on that skill. Okay. I want you to be able to communicate to me using handwritten math that you understand the concepts and the calculus and the skills and everything like that. So thank you for that question. Speaking about exams, since we've been going that direction for a little while, most of the credit for the class is going to be exam based. I think, again, I'm just trying to remember what the syllabus says. I changed these numbers from what I've used in previous semesters, so it's not a little fuzzy. I think it's 10% homework, and then we'll have 2 shorter exams, which will end up being the first exam and the third exam we take will be each worth 15%. And then we'll have larger exams, a midterm and a final, that'll be worth 30% each. Okay. Oh, you got your, yeah. Okay. So, technology wise, Blackboard is not hosted on campus. So if campus internet breaks, you have a way to get off of campus internet, and still get into Blackboard. That's why that works, and everything else seems to be messed up. Anyway, so we're gonna have a midterm and final that count for more. Exam formats are something that I will discuss a little bit more clearly when we're closer to that. For us in here, all of our exams are just going to be regular in-person exams. Okay, so we'll take the Friday, if there's a Friday that week for us to use, and just sit and have an exam. Which is good news for you, because that means you'll have a 50-minute midterm instead of an hour and 50-minute midterm, which is what the online people get. But I can't give them in-person tests for the other ones, so that's their benefit. Anywho, make sense? Okay. Sorry. It's very weird to have a syllabus discussion without the syllabus in front of me. Okay, so the question is about the syllabus. There's something called measurable course outcomes. That was something that had to be added to our syllabi several years ago at this point. It was some policy thing. They don't mean, they're not really for the students. It's not something that you'll interface with directly. There's a link earlier in the syllabus that's supposed to go to like the Calculus 3 page that has like department-wide policies and information about the class. If you want to look at what the outcomes are, follow that link, and they should be listed on that webpage. But it's not something that you need to have. When that policy was instituted, it was not made clear to us how those outcomes were to be checked. So they're in my syllabus just as this section is, these sections or these exams correspond to these ideas, so that that wasn't a mapping that I had to figure out later after the policies had been written a long time ago. Okay. All right. I think. Does anybody have any other policy type questions at the moment? Yes. Yeah. Okay. So for stuff that I ask you to turn in Blackboard, what I will ask you to do is handwrite it, and handwriting counts tablets if you have a tablet type thing, and then turn it into a PDF file, preferably. If you do that by taking pictures of paper with a phone and then using an application, that's fine. And then submit that into Blackboard. I may decide later to have more specific instructions about this in terms of maybe making like one problem per page or something if I get a lot of work that's very cramped and hard to read. So keep an eye out for a subsequent announcement if I need to adjust that. But if people police themselves well and your stuff is organized and I don't have to make comments about it, then that's the easiest way to handle it. I have other people that I work with who do things like they'll make separate problems in Blackboard and make people submit different files for different problems. I don't want to have to do that. Sounds like a lot of work. So if we keep things clean, then we'll do it that way. Other stuff? Yes. We'll say yes. If if the quiz ends up being I'm asking you to turn in something on Blackboard at home, then I can't reasonably police that. So I might put technology questions on the quiz. So like if the quiz is basically having you turn in a few of the homework problems, then I will expect you sometimes to use technology. Okay, but that'll be something that we demonstrate in class and go forward with. If it's if you are taking a paper test in this class, electronic devices are banned. That's the policy. Anything else? All right. Okay. So there's an interesting thing that happened a few years ago. From the way that we teach our calculus classes and some other related classes here at the university. I a very long time ago was a freshman here, and they allowed you to do something silly, or at least is now considered silly, which is take calculus 1 and physics 1 at the same time. Uh, this proved to be something that they decided that they wanted to change because there were a lot of people who got to physics 1 who could not make heads or tails of vector notation. So a lot of you, I would imagine, had the experience that you weren't allowed to take physics 1 until you were enrolled in calculus 2. The reason being that you cover the first 4 sections of chapter 12, which happen to be about vector notation in calculus 2, and then they allow you to continue on physics 1. So that leaves this class in a bit of awkward spot where all of chapter 12 probably wasn't covered. All right. Now, for us, the last 2 sections of chapter 12 are the important ones because they're the ones that introduce some of the ideas that we're going to be using going forward when it comes to equations of lines and planes and some other surfaces. So what we're going to do for today and a little bit of the rest of the week is talk about in very broad terms the material from chapter 12. okay, to get us set up. When we come back on Wednesday, what we're going to do is we're going to cover 12.5 and 12.6, but we're going to go kind of fast because there's really only a couple of main ideas from those sections. All right. But the thing that you need to make sure that you're double check yourself on and use some resources to do is feel comfortable with vector notation. All right. You should feel comfortable with vectors. You should feel comfortable with dot products, and you should feel comfortable with cross products. Okay. So we're going to talk a little bit about that today. I would have some things that I would show you if the internet worked to help out with that, but the internet is still not working. Oh, wait. Oh, is the internet working now? Have I shamed it? Hold on. Maybe I said enough bad things about the internet that it decided to work. Well, that's fun. Okay. All right. This is like just in time getting the internet back. All right. So one of the resources for this class is a set of online notes that I and a couple of my colleagues put together. Included in here is some material from the other sections in chapter 12 to serve as a review and as an overview of kind of how I view the material. Okay, I'll put a link to this in Blackboard. It's just a website that hopefully won't get taken down because we've had some weird problems with websites disappearing. But okay, so if you want to read through and see some examples beyond what's in the textbook and stuff, some of this material is pretty similar to what shows up in the text, but we have some other examples here, and then also some explanation of notation, which is one of the most important things. Okay, so read through this, make sure these things make sense, remind yourself about stuff like the distance formula for three-dimensional space. There are some exercises to check yourself against. All right, equation of a sphere. If you click on these things, you can see the results of some of these computations and other things like that. Okay. What I want to spend a little bit more time talking about is vector notation and the dot and cross product stuff that I had mentioned previously. Okay. Since we have the notes here, I'm just going to use these kind of as a guide so we can quickly go through things and you can check these out on your own time to make sure that stuff makes sense. I very, very highly recommend that you watch this video. Okay. 3 Blue 1 Brown is a wonderful channel that covers some math topics and is very good at doing visualizations. There is on that web channel a series of videos called The Essence of Calculus, all right, which will visualize and contextualize some ideas from calculus in ways that you may not have thought about completely, but is a very useful thing to have seen, maybe not when you're in calculus the first time, but after you've taken calculus 1 and 2, to go back to revisit the ideas to kind of put it all together, all right? This video here is the first video in a similar series called The Essence of Linear Algebra, having to cover vectors. And in this video, the author, Grant Sanderson, goes through and talks about kind of 3 different pictures of vectors. All right, there's the physics picture, which is the arrows. There's the what he refers to as the computer science version of the picture, which involves basically just a list of numbers. All right, and then there is the math version of the picture, which is this vector notation stuff. All right, where there's just a symbol, and this symbol is a thing that we call a vector, and it has the properties that vectors have, whatever we say those are, right? Because that's how math works, right? We have a thing, we give it a name, we say that it has these properties, and then we figure out what the consequences of those rules that we just made up are. But this and some of the subsequent videos is very good. I do recommend that if you're in linear algebra or have taken linear algebra, that you go through and review these videos. All right, you can watch them kind of contemporaneously with the subjects as you cover them in linear algebra to give some context to stuff. But this first video is useful regardless of whether or not you're in linear algebra itself. All right. And then the other thing that I try to carefully go through here is the different types of notation that you will see. All right. It is an unfortunate truth that once we get to vectors, there isn't a lot of agreement about how the notation should be used. All right. You're going to see a lot of overlapping notation or notation that's not consistent. And the thing that you need to be aware of as students is the fact that there's some stuff going on here, some things to be paying attention to so that you can understand what you're reading. All right. Different people have different preferences, and those preferences vary more greatly kind of at this stage of math. All right. So here I try to explain some of these preferences as well as my preferences, which will be the ones that I use here in class. Okay. One of the types of notations that you'll see is this type of notation, where you'll see an arrow over two named points P, Q, and this is the displacement vector from P to Q. All right, so you have a couple named points, you'll have this displacement vector. Now, a displacement vector, once we think about it in terms of being a vector, vectors have direction and magnitude. Okay? Every vector that has the same direction and magnitude is considered to be equivalent. All right? We don't care about its placement. All right? Placement is irrelevant when it comes to how we think about vectors. They're just direction and magnitude. Okay? And so we have a couple of different notations for this. If we're using a single symbol to represent the vector, then sometimes we will use an arrow over or a harpoon. Sometimes people only draw half of the arrow, or one of the sides of the tip will be missing. All right. Both of those things are perfectly standard notation. Pretty popular amongst, say, engineers I've seen, is that tends to be, engineers and physicists tend to use the arrow over type notation. And then in print, often, and this is easier to see when you're not looking at a screen that's several feet away from you, if you're next to it. This is bold-faced, okay? And in print, the bold-face vectors are typically the way that they're written, all right? So if you're reading a textbook or you're reading an online resource, the vectors should be easy to pick out because they are the things that are written in boldface. And that's usually pretty consistent. But people have a hard time writing in boldface, so that's why we end up with the other types of notation with the arrows over or things like that. Okay. In this little block quote here, I line out some things. All right. Now, one of the things that I will be doing, and this is a personal thing for me, is when I write my vectors, I underline them. Okay. I just find it more convenient to have the marking under rather than over because it keeps it out of the way of things like exponents or other symbols that I have to write. So that's for me, I will underline my vectors. Okay. Unless they are hatted vectors. If they're hatted vectors, I'll write the hat. Okay, but when I write hatted vectors, I mean something specific. Usually what we will end up calling canonical basis vectors, which we should remember what those look like. Okay, so these are the canonical basis vectors in 2D and 3D. All right, it's important to remember that it's changes based on what context we're talking about. I also, since I've taught linear algebra a couple of times, tend to write things as column vectors. All right, sometimes I will cheat on this when it's inconvenient to write things as column vectors, but whenever I'm thinking about a vector, I always think about it as a column vector unless I have a reason not to. Okay, this is something that if you've taken linear algebra or if you take linear algebra in the future is a good habit to develop. Okay, the way that our notation works kind of in the background, sometimes this is obscured by the way that textbooks are written because people are trying to save space. But they're all column vectors. Okay, so if I write something like this, those commas means that I should have written a column. Yeah. Again, this is not something that's necessarily universal. All right. Because people have different ways of doing stuff, but that's kind of the idea. All right. It's the best practice is to assume it's a column vector unless you're told that it's not. All right. So there are some pictures that go through to remind everyone how vector addition and vector multiplication work. All right. Here, again, this goes through some of the explanation that I was just mentioning. All right. Default is a column vector. Okay. It is typical in notation to use a bold-faced version of the letter to represent the entire vector, and then to use a non-bold-faced version of that same letter with a numerical subscript to indicate the components of that vector. So here I have a vector v with n components. So n numbers make up the quantity for this vector v, and they are ordered and given this way. All right. The one that I was making fun of a second ago was just the so-called just plain lazy version of the vector, right? That doesn't have this transpose here telling you that this definitely should be a column vector. All right, they just present it as a list of numbers, but they called it a bold-faced V, which is a thing that should be a vector, right? This is part of the problem that I was referring to earlier when I was talking about reading math. All right, when you are looking up online resources or textbooks or things like that, you need to be familiar enough with the particular source that you're looking at because they will make choices based on preferences that affect these sorts of things. and it's not consistent. Different engineering textbooks will tell you different things. If you look up stuff in computer science books, you might get other looking information. All right. Our textbook, Stewart, has a weird notation that it uses. Okay, it uses angle brackets to talk about its vectors. Okay, which is not a notation that you tend to see in other places. All right. The nice thing about this is that if these angle brackets show up, it means that you are definitely certainly talking about a vector. All right. This means a point in space without the bold-faced V, just a parenthesis and a list of numbers. And this means that you're talking about a vector and its components. So that is nice. But if you're going to get in the habit of using one of these notations overall, this should be the one that you pick. Okay. It is the one that takes the most space, but it's the one that is the easiest to read because it forces you to space your writing out the most. All right. And if you happen to be, like me, a person who is privileged enough to have access to digital paper to write on, the cleanest, easiest way to keep track of what it is you're doing. All right. Some more stuff about vector arithmetic and some practice. All right. I mentioned earlier the math picture of vectors and rules. We call a thing a vector and we say it's a vector if it follows these rules. Okay, these are the rules. Vector addition commutes, vector addition associates. The 0 is the additive identity for vectors. Every vector has an additive inverse. Scalar multiplication distributes over vector addition. Scalar multiplication distributes over scalar addition. Scalar multiplication associates, and 1 is a multiplicative identity for scalar multiplication. Anything that you can come up with that follows these rules is a vector. That is a very large class of things. All right. It includes arrows in space, which you would expect that have the rule for Euclidean distance, which is the way we normally measure distance, right? In 2D space, 3D space, 20-dimensional space, whatever you want to say. It also counts things like continuous functions, continuously differentiable functions, okay? Complex numbers, all right? Weirder things that you wouldn't tend to think about. Now, we're not going to go deep into these kinds of things, and the vector spaces that we're mostly going to be concerned about are 2-dimensional Euclidean space and 3-dimensional Euclidean space, because we are here to study vector calculus. But know that this is a very broad definition of things, okay? I mentioned earlier the idea of standard bases, okay? And we have here the canonical unit vectors for 2D and 3D space, I hat, j hat, and k hat if we have 3D. All right. One of the things that the textbook will test you on often is your ability to jump back and forth between component notation and canonical basis notation by presenting you different forms for how problems are written. Okay. When you're communicating your answers to me, I don't care so much if you give me component form or if you give me canonical basis vector form. Component form is usually easier, but you need to be able to flawlessly translate between these types of notations. That's part of what we're asking from you for prerequisite skill. All right, and there's some application type questions here too. All right. Yeah, I'm also having to remember that this clock is wrong. It's on my computer. Okay. All right. All right. A couple more sections here. there's the dot product, which there's some explanation going on here. All right. In a linear algebra class, instead of using I hat, j hat, k hat, you would maybe instead use a bold-faced E subscript 1 to indicate the canonical basis vector for the first component and the canonical basis vector for the second component, and so on, so that you don't run out of letters when you decide to have a gigantic dimensional space. You can just have the 17th canonical basis vector. It would be E sub 17, right? There's some other stuff here. Another very useful video from 3 Blue 1 Brown talking about linear transformations. This is not stuff that I expect you to remember all of, but it is a little bit of that linear algebra context that goes behind what is a dot product, how does it work, and why is it important for calculus. Okay, so don't get freaked out. I know there's a lot of notation here, but it's just because we're not leaving stuff out. Okay, your book doesn't talk about this. All right, so there's some more stuff about linear transformations. The reason we talk about all that linear transformation type stuff is because it makes dot products easy to understand. All right. A dot product basically can be thought about as a projection, okay, or as a component for a projection. I have a vector v here, all right. I take its dot product with the vector p, and what happens, I take its dot product with vector w, and I can, using a dot product, figure out essentially what the shadow of v that is cast upon w is. Okay, so if I look at the tip of the vector v and I draw the shortest possible line from v that comes down here and touches the vector for w, then the shape that I get left is the projection of v onto w. Okay, the way that we represent this mathematically is through the use of a dot product. This part here is v dot v, the square root of v dot v times cosine theta. And this is explained in more detail down here. Some people who really want in this room. All right. Anyway, there's more in-depth linear algebra stuff here for you to go through. For you, the most important thing is that you understand what a dot product is, how to compute a dot product, and that dot products represent projections. Okay? Because we will use that projection property for us. All right, there's one last bit. We're not done yet. Oops, I did not mean to do that. Go back. All right, the cross product is a very short section. Well, it's long here, but the cross product is something else that you need to compute or be able to understand how to compute. We compute the cross product using minors most of the time. Okay, so remind yourself of this process. Because there's the computing a determinant process, which is just a linear algebra thing. And then there's the computing the cross product process that people use as a shorthand for doing this computation. Okay, now there's two ways to write this. In this page right here, it's written in a column format where you have I, j, k, and then you have these three coefficients, -3, -1, 3, written as a column, -3, -1, 3. Okay, and then when you do the expansion by minors, you always expand on the row that has the letters because this is bad notation that doesn't actually mean anything, right? This is just a placeholder notation. Okay, there's another way to write this where instead of writing it like this, you would write IJK across the top, and then the second row would be -3, -1, 3, and the third row would be 8, 8, and -2. Okay, I don't care how you write it. I usually write it in the row format too, but I didn't type this particular example in, so it got written in the other way. They both mean the same thing. So it's just a heuristic for remembering what it is, and then this is that computation worked out symbolically so that you can remember what's going on. All right. Do not forget this minus sign. Okay, people will forget about that minus sign. That minus sign comes from this, from the determinant computation of computing a determinant via minors. Okay, it's in, regardless of how you write it, there's a minus sign in the middle. So there's always a minus sign on the J. Okay. All right. So we'll call it there for today. I'll post this link in Blackboard so that you can take a look at it, but go through and review these things. We will next class talk about the remaining 2 sections from chapter 12 concerning equations of lines in space and some stuff about some surfaces. All right, take care.